Good morning. Today we're going to look at an experiment to measure the thermal conductivity of a metal by using a Searle's bar type method. So what do we mean by thermal conduction? Well, some materials such as metals are a good conductor, largely due to the fact that the clouds of free moving electrons can carry the heat from the hot part up to the cold part. Other materials are poor conductors of heat, such as wood. These don't have the same conduction mechanisms available and as a result are much poorer conductors. So we want to give this property a number. We call it the thermal conductivity, the symbol K, and it's measured in watts per meter per Kelvin. The higher the value of K, the better it conducts heat. It's defined by the heat conduction equation, and which we can see illustrated in the diagram below. So imagine we have a metal bar. One end is held against a hot surface at temperature T2. The other end is held at a cooler surface, temperature T1. What we find is that heat flows along the bar from the hotter surface to the cooler surface. So if we have a cross-sectional area of the end of the bar A and the length of the bar X, we can use the heat conduction equation to show that the rate of flow of energy, Q over T, which is a power, along the bar is proportional to the cross-sectional area, the temperature difference between one end of the bar and the other end of the bar, and inversely proportional to the length. The constant of proportionality is defined as the thermal conductivity K. The negative sign appears in the equation simply because as the temperature goes from cool to hot in this direction, the energy flows in that direction. Note that we've made some assumptions. The first is that we have a constant temperature gradient along the bar. So the temperature varies linearly as you move along the bar. This situation arises when all the heat flowing into the bar flows in parallel along the bar and out of the other end. There's no heat lost out of the sides of the bar. This implies that the bar is perfectly insulated. Note that if this isn't the case, the temperature will drop off more steeply at first as you travel along the bar as heat is lost from the sides. So in the uninsulated case, you need to use a differential expression of the equation. The next assumption is you've allowed long enough for the system to reach a steady state, which means that at any point along the bar, the temperature remains constant with time. Implicit in all this is that the bar has a uniform cross-sectional area along its entire length. We can use this definition as a means of measuring K. This is the approach that was taken by George Searle, a British physicist born in 1864, who used a method very similar to this, except where we're using electrical heating, George Searle used steam heating. Otherwise the process was roughly the same. So here's what our experimental arrangement looks like. We have a metal bar, which is heated at one end by an electrical heater. The current flowing through the heater and the voltage across the heater are measured so we can work out the power that's being provided by the heater. At the other end of the metal bar is a constant temperature heatsink, which is an iced water bath. The bar is insulated all along its length so that the heat provided by the heating element travels linearly down the bar and isn't lost out the sides of the bar. The temperature is measured at 2 points along the bar, a fixed distance x apart. So we have the temperature at this point and the temperature at this point. We can easily measure the cross-sectional area of the bar. We leave the system running with heat being provided until the temperatures stop changing and then the system has reached a steady state. Now we have all the information we need to find the thermal conductivity K. So let's have a look at our equipment. At the heart of the experiment is a metal bar. You can just see the end protruding out from the insulation. At one end is an electrical heating element that's powered through this cable. The other end is available uninsulated, so we can place that against the heatsink. There are two thermocouples, these green wires. One is in one part of the metal bar, another is further along the metal bar. The heating element is powered from a power supply through this circuit breaker, whose purpose is simply to prevent us burning out the heating element by taking too much current. The temperature on the thermocouples is measured using this unit, which measures two temperatures, temperature of each thermocouple, and it will show it on the display here, and you will also be able to read it out through this USB port onto the computer. The heatsink is simply a jar of iced water which we will surround by an insulating jacket to stop the ice melting too quickly. The heating element is powered by this power supply. The heating element is comprised of a power transistor, which we're kind of abusing, and so it's easier to actually control the current, to control the power being dissipated in the device rather than the voltage. The current flowing through the power transistor is registered on the ammeter on the power supply, which I've verified gives an accurate representation of the current actually flowing through the device. But because there's some voltage drop between the output terminals here and the output of the circuit breaker, we can't use the voltage display, which in any case isn't accurate at very low values, and so we read that on a separate meter. If you look closely, you can see there's a ground terminal with a bar to allow you to connect the ground and the negative terminal together. This connects the negative part of the circuit to the mains ground. In this case, we want to make sure that that's disconnected, because if we don't, we've got multiple places where the mains ground is connected to the equipment, e.g. this would be a place, the plug on the circuit breaker would be a place, via the USB ports from the thermocouples through the laptop and through its mains, and all these earths can cause earth loop type problems. So you're better to avoid all those to get more stable readings by making sure that the earth at this point, the mains ground, is not connected to the negative terminal and that the two power supply terminals are allowed to float. So now let's have a look at all the equipment connected together. So let's have a look at the equipment. In the center we have the sample, which is wrapped in black insulating foam. It's a metal bar with two thermocouples spaced along its length. At the top is a heating element, and at the bottom is an open surface, non-insulated, which is inserted into the top of a constant temperature ice water bath. The heating element is powered by this power supply. It's run in constant current mode because it's easier to control the power in the semiconductor heating element than trying to use a constant voltage. The current readout is on the left. We don't use the voltage readout on this instrument, firstly because it's not very accurate at low voltage levels, and secondly because the output voltage is through this current limiter device, which is there to protect the semiconductor heating element. Instead, we read the voltage at the output of this unit from those leads with crocodile clips you can see there, and that voltage is displayed on this meter here. The dual thermocouples in the metal bar read onto this display here, which is also connected into the computer. Right, we'll insulate the ice water bath to try and stop heat loss. And we will lower the sample into the ice water. The purpose of that is to try and keep the far end of the rod as close to zero as possible. So to read the thermocouples, we'll use this data wrangler software. We'll start with a blank sheet. Time, T1, T2 for the temperature of the two thermocouples, and then T1 minus T2 to give us the temperature difference. We'll calculate that column from column 2 minus column 1. Go. Now let's connect to a data source. Connect to the USB device. And set up a graph. Okay. So we'll set up the graph to look at the temperature difference. And we'll start to gather data. So with the end of the sample in the ice bath, we can now increase the current. This is providing power to the heater, and it's safe to raise the current up to about 700 milliamps. Now we need to wait until the graph reaches a steady state. As you can see from the graph, the line is now roughly horizontal and it's reached a steady state. Looking at the instruments, we can see that we're running at a current of 715 milliamps and a voltage across the heating element of 2.22 volts. We can stop the graph automatically redrawing, and we can stop the data collection. So now the system's reached a steady state, let's analyse the data. So we'll delete all of this older data and keep only the last 100 seconds. And now we'll perform some quick statistics on this data. So we'll select Data, Quick Stats. So concentrating on the end column, which is the temperature difference, we have a mean of just over 3 and a standard error of 0.015. So let's calculate a final result. Starting with our equation Q over T equals minus Ka T2 minus T1 over X, where Q over T is the power developed by the heater, which is equivalent to the electrical power delivered to the heater, IV. T1, T2 are the temperature of the two thermocouples, which we'll express as delta T. X is the distance between the thermocouples, and A is the cross-sectional area of the bar, which is pi d squared over 4, where d is the bar diameter. Rearranging all this gives us K equals 4x IV over pi d squared delta T. So we can plug in all our values to give us a final value of K equals 202 watts per meter per Kelvin. The data book value for aluminium is 236 watts per meter per Kelvin, but this is for a high purity single crystal, and our less pure sample would be expected to give a number lower than that, which it does. So it's in reasonable agreement. So let's look at the errors in our value. We have our rearranged equation, and delta T is the difference between the thermocouple temperatures, which following the treatment in Hughes and Hayes gives us this expression for the standard error alpha K in our measured value. We can look at typical accuracies of the different measurements for X and D and for the current and voltage readings, but we'll see that the error in the thermocouple reading, delta T, will dominate. There are several reasons for this. First, type K thermocouples are not particularly accurate. The datasheet suggests that they're good for kind of plus or minus 1.5 degrees C. Additionally, we have a difference in two similar numbers, and when we come to look at the errors in that, we find that the percentage error is very large compared to the size of the number. You will probably get better tracking than this between pairs of thermocouples from a similar batch, but we'd need additional experiment to work this out, which is beyond the scope of this video. That said, I wanted to get a rough idea as to how well my two thermocouples are matched by running the experiment again, only this time insulating the entire sample, keep it at room temperature and provide no power. So we'll reset the software, we create a graph with the least squares fit line, and we start collecting data. As we can see from the graph, there's a systematic difference of about 0.6 degrees C between the two thermocouples, and a random jitter of about plus or minus 0.2 degrees C. A full treatment of these errors is outside the scope of this video. So that just about wraps it up. Thanks for watching.